Hi, my name is Ariel, and I'm a data scientist at the University of Washington eScience Institute, and with support from the Sloan and Moore Foundations, and together with our partners at NYU and at Berkeley, we're building environments for data science within academia. And today I'll tell you about the project that we're working on this summer as part of this, which is a project to do data science for social good. The idea in general is that organizations devoted to social good collect data. And if we use data science to mine these data, we might provide some value to these organizations. In the particular context of our DSSG, this is also an opportunity to train data scientists from a variety of different fields. This is a premise that has been tested before at the University of Chicago. There are other places that have followed. In Atlanta, there's a similar summer project going on for a few years now. And there's that similar premise is also sort of approached outside of academia. There's an organization called DataKind that does similar projects, applying data science to social good. Specifically, our DSSG 2015 is a 10-week internship program. We have 16 students from a very broad variety of backgrounds, different fields, different levels, ranging from undergrads to graduate students. And then we have project leads that come and work with us from partner organizations, and they serve as the data owners and also domain experts on the questions that we're approaching in these projects. And then data scientists like myself work alongside these teams to look at the data and produce something out of those. The projects that we're working on this summer, there are 4 projects. One of them is aimed at predicting permanent housing for families in homeless shelters in the Seattle area. That's in collaboration with the Gates Foundation. Another project is about mapping out well-being in different neighborhoods in the region in collaboration with Third Place Technologies. We have 2 projects in collaboration with the Taskar Center at the UW. One is about building an accessible street graph, a street graph that also includes accessibility information. And then another one about optimizing the deployment of Seattle paratransit. So these are the projects that we're working on. Unfortunately, we've only been working on them for a few weeks, so I won't show any results now. I'll just tell you about this and hope that you follow up later. During the time that they've been with us, the students, the interns, have gone through various tutorials, learning how to do data science. Here's Jake teaching them about SciPy. And they've had, of course, in a summer project like that, you have to have a little bit of fun. So they've done various team building exercises. Here they're doing a scavenger hunt in the library and enjoying the Seattle sun. But mostly they've actually been sitting around like this with their computers and puzzling about these various data problems. I'd like to thank, of course, our collaborators, these other organizations that have come to work with us. Our sponsors, of course, the DSSG students, and all of you, and I have plenty of time. Oh yeah, stay tuned. There's a link over there. You can check out our results later this summer. For now, we don't have much there.
Thank you very much, Ariel. I hope that doesn't imply that everyone else is doing data science for social evil. All right, next up on the deck is Daniel Soto. If you could come up, please, now. Thanks. And right now we have someone who's going to introduce himself.
Okay. I am Rowan Cockett, and I work at 3 Point Science, and we are a web development company, and we do education, and we also do 3D geoscience visualizations. So we've developed some sort of cool tools that allow you to interact with 3-dimensional data in space, and also some presentation tools, so being able to change perspectives and things like that. So we've been developing this JavaScript library for a couple years, and so what I want to show to you is what we can do with points and lines and images in Jupyter. So here we have some points, we have a line, and we have an image. So what I'm going to do is load this up into the IPython notebook, the Jupyter notebook. So this is getting an ID and making a request to the server. And now we have this in the notebook. And the cool thing about the notebook is it's already awesome. So we can ask for the path, and then we can set the path like this. And so the image updates right away. And so I've named these points as well. So we can change this to a w.source and a w.sync. And so that changes that. But really, we want that to update every time we change it. So let's make that into a function. And then we can hook it up to the widget and func and the source and the sync and close the bracket. And now when we change this, we're running some Python code, and that's updating the visualization live. And that's kind of exciting. So we do a lot of work in the geosciences in education, and especially with solving direct current resistivity and doing PDE solves. So we can hook this up to the visualization like that. And so as you can see here, if I drag this over here to the top right, run this code again, it changes where that source was. And so what we can actually do, what we want to do, is be able to directly interact with all of this. And so we can just remove that hook and then put this in here by that. And so now what we've done is when I change these guys, it's going to solve a PDE in real time, and we can interact with this in the notebook. And so this is, we've loaded up something from JavaScript, injected it in, and so this is sort of a really interactive way to run your own code. And so now all of the widgets are embedded directly in the IPython notebook. And so that's where we're sort of at. So again, where we are is creating this counterpoint library, which is a lot of HTML, CSS, and then wrapping it in Python, bringing that over to the Jupyter kernel so that you can interact directly with your code. And the sort of next step on that is to bring this into some interactive documents that we're working on. So if you want to know more, go to 3point.xyz, and that's what it looks like right now. And so give us your email, and we'll say when it's ready. So thank you very much.
Thanks. I should have brought my binoculars. 3 points is kind of hard to read from back there. OK, so next up on deck is Blake Griffith. And currently, we have Daniel Soto.
Hi, my name is Daniel Soto. I'm an assistant professor in the Department of Environmental Studies at Sonoma State, north of San Francisco. I'd like to talk to you today about the idea of replacing the calculator. And the kind of sub-idea is, how early can we introduce literate computation? Most of us probably came to Python as fairly mature scientists. I'm trying to think, how early in the training process can we get some of these tools and some of the values that we have around reproducibility and transparency? So my vision, once I'm done training a student, right, would be that students come to expect implementation details for anything they encounter, right? They expect to see the math actually done, no matter how simple the computation is, right? And wouldn't it be nice if everyone in society demanded evidence for every claim? Now, what I realized was, thanks to this community, I try to have those sorts of values in my own work, right? Reproducibility, transparency, the ability to see what I'm doing. As I started teaching, and I'm new, this is only my second, I've just finished up my second year, I kind of understood that what I was doing was actually teaching worst practices in some of the ways that we do this. So what do I mean by that? So the main tool we use is the problem set, right? So how many people have not done a problem set? Okay. Right, so the written part actually sort of adheres to the basic rules of you should state your assumptions, you should write out what you're doing, you can see the flow from sort of a symbolic representation to what you're supposed to have. The computation, the last step where we actually get a number in base 10 is completely obscured from what's going on, right? Because we use a calculator, right? That's the ubiquitous computation tool for students, right? And so you go under the cover of darkness and you type something in and then you write that down. And that piece, that really important piece is gone. So when did I start to discover this? It was actually in my classroom in the first year of teaching. I was seeing stuff in an introductory type math course where I was just getting, everything was set up right, and then I was getting wildly different answers. And I sort of asked myself, what's going on? And so I actually went around and observed people using their calculators. And I was shocked. I grew up playing around with calculators. Not everyone does. And these are students that don't recognize the term scientific computation, even though that's what they're doing. So then I begin to ask myself, like, how can I improve their computation ability, right? Even though maybe they're not going to be attending this conference at any point in their life, but the basic tools, I think, these sophisticated tools could be used in simple ways. So what about our first computation tool? Why do we use it? It's simple, it's rapid, there's an API cheat sheet right on the front of it. It's got a lot of reasons why it's nice to use. The drawbacks are basically there's no record of anything, and there's this opportunity for transcription errors, right? So if you use something like a Jupyter Notebook, which is basically a literate computation environment where you can document what you're doing and you have a record of everything, my claim is that you can use these with minimal disruption in the classroom, basically thanks to the efforts of this community. So a year ago, I tried with an environment that was in Python 2, and the minute we went through from future import division, like it was just chaos in the classroom, and we had lost instruction time, right? So, but now things are to the point where you can really use these quickly. They allow reproducibility, and what I'm trying to do is use them to create the gradual introduction of variables and other abstractions, right? Without hitting them with the full force of every abstraction ever and then asking them to do something, just sort of introduce this as a computation tool. So I've been experimenting with these Jupyter tools in early classes, and again, I present them as, this is the calculator app for your notebook. I don't use the word programming because that can be emotionally charged for a lot of students. It allows them to document their calculations and get feedback on the methods. I can see the keystrokes that were done in a Red Bull-fueled haze in a dorm room somewhere, but now I can see them. Full disclosure, I'm using Julia because I don't have to type any import statements. There's already all these great math functions in the global namespace. Eventually, we move them up to Python, but again, I'm trying to minimize the cognitive burden, right? So thanks again to the community for making tools like this. This is not an exhaustive list. I'm sure there's somebody working on one right now. But the ability to get onto a URL and have a fully functioning environment within 3 clicks and 30 seconds makes it so that we can introduce these tools early and earlier to students in the classroom. So thank you.
Thank you, Daniel. I definitely came to scientific computing as an immature scientist. TI 1989. All right, next up on deck is Southside.
What's going on here? Okay. So I'm going to talk about Dask distributed today. Some of y'all might have heard about Dask from Jim Christ's talk. It's a way of doing parallel out-of-core locked algorithms. We have a thing called a Dask array that's kind of like a parallel out-of-core NumPy clone. Dask distributed is a way of executing Dask graphs that are made by Dask array in a distributed memory environment. So first of all, setting up a distributed memory environment isn't really trivial, so I was going to go over how we were going to do that, and I actually can't see this on my screen, so we would do Continuum has a tool called Anaconda Cluster for setting up distributed memory environments and managing them. So we could use can you guys all read that? Yeah. Okay, cool, now I can read that. So, a cluster, create, and so this would launch several EC2 instances, but I already have them running. This is managed by a little profile directory, and yeah. In here, that specifies the kind of Amazon instances and how many of them. So I'm going to use 10 Amazon instances, and I'm going to run, I installed an Anaconda notebook on them. Like that, and all this stuff's already installed, so I can open the notebook in my browser. So I gotta move this browser window over to here where I can't see anything. So now I have a 10 node cluster running with a IPython notebook running on the head node. And I can import a Dask distributed client to connect to the scheduler, which is gonna deal with handling where the tasks go and sending them out to the workers so that I can execute my computations. So this creates the scheduler. This is just showing I got a bunch of workers. There's 18 of them. So 2 for each node for each core minus the head node. And then, I don't know if everyone can see that, sorry. Where are we at now? I can't actually see that either. So I'm going to import Dask array here and create a 10,000 by 10,000 array and then compute the mean along one axis of it. So that's a pretty big array, right? NumPy could do that, but it would take a minute. But here it should only take a second. Below that, I create a 100,000 by 100,000 array, so like 10 to the 10 elements. I'm not gonna do that here because it takes about a minute and something seconds to run, but that's a lot faster than what NumPy would do on one machine naively. And so we also have a few, other than Dask array, we have other collections like Dask bag, which is good for handling like lists or ordered, yeah. So Dask bag is like a set, but it can have duplicates, so it's unordered lists basically. So I can import that here, and I'm importing a bunch of, I'm importing 1 month of data that GitHub provides from githubarchive.com. It's about 5 gigabytes. That's what one of the little JSON things looks like. Yeah, and so Dask bag can also work on Dask distributed to do this, and we can work on about 5 gigabytes of data to do like a frequency count to see what kind of events happen with the GitHub archive on the GitHub archive data the most, and that computation takes about a minute to process 5 gigabytes of data too. So yeah, that's it.
Thank you, Blake. All right, up next on the dock is Andrew Reed. And currently we have Katie Huff, the illustrious.
It's true. I'm Katie Huff, and I'm a very serious scientist. I'm a nuclear engineer, as many of you discovered this morning when I forced you through the mathematics of nuclear reactor kinetics. This talk is not that. In the great tradition of slightly goofy lightning talks, I was talked into last night giving a talk on something that I made much simpler with my skills that I learned from SciPy. My wedding. So I got married this year. A lot of people are getting married this year. It's a new thing that is a lot more people are now allowed to do. Woo! Yeah, and weddings are really great. They're great, big, complex events with lots of logistics. And the people doing them actually have to do those logistics, which seems like a lot to do. I have a pretty long to-do list, so it was kind of hard to face. I thought maybe we should go to the courthouse instead. But we decided we would probably do it, so I had to pick some colors. You know, I'm not a designer. I don't design websites. I write code, right? And so I went to the internet, and I let this tool called Pictolicious take my image and turn it into a color palette. And the image I chose was the picture of my venue so that I could not have to buy any flowers because everything would just match the room. It was a glorious life choice, so that I automated that. I'm also not a web designer. So whenever I really want a website that's not Sphinx documentation, I go to GitHub. And I fork someone else's website, which is beautiful HTML5. And in this case, so too I did that. It turns out there are hundreds of people on GitHub who were somehow assigned to make the wedding website. If any of you are going to be that person, I encourage you to do this. You can fork my wedding website if you like. It was very pretty. We won't go into that now. You also have to have a lot of paper. There's a lot of paper involved in weddings, right? This isn't Python, but it's LaTeX, and I did all the paper stuff with templates out of LaTeX, and they all matched because I'm too lazy to change one template to another, so the program looked like the invitations, looked like the menu. It was great. So I would encourage you guys to do that too. You know how to do it. Now finally, the really tricky bit was the invitations, okay? So many of you recognize this Jinja template, dear guests. And what I did was I took a Google contact spreadsheet of the tab-separated values of all the people that I intended to invite to my wedding, and I combined them using a little OpenRefine. Anyone use OpenRefine? It's a cool tool for cleaning up your ugly data. And cleaned up my contacts, combined them into families, and sent this Jinja template out to encourage them to join my wedding. So with this Jinja template, so that just populates the email that I would send. And to actually send it, you use the MIME syntax. So you need there's an API behind all email, right? And actually, that's how many of you have received emails from me and other program coordinators and proceedings chairs and everything from SciPy is through these Jinja templates. So I just grabbed this script, which the same script that I have used for SciPy in the past, and subject, invitation to my wedding, stuff like that. So pretty fun. So I used Python to invite people to my wedding. Once they responded to the Google RSVP on my website, which I forked. This is the tab-separated values. So you just have the Testerson family and their email addresses, and any particular message will fit into that Jinja template. Okay, anyway, so then months pass and they've all RSVP'd to your wedding, and you have to remind them that they're coming and how to get there and stuff. And so I did this, if they were coming to the welcome dinner based on the Google spreadsheet, right? So I just loaded the tab-separated value spreadsheet from Google. That my Google form generated. And if they were coming to the welcome dinner, then I gave this message, and if they're not, I just don't talk about the welcome dinner at all. So that's how the reminders were set up. It was a really excellent wedding, but one of the best parts was actually, I would strongly recommend that you have an Anthony Skopats there. And I would also recommend that he give a NLTK-generated talk based on the emails you have sent him over your many years of friendship, which happened. And that is all. Not all of it is on this repository, but the master branch holds the useful stuff. The GH Pages branch holds the website.
Thank you. Thank you, curly brace, speaker, close curly brace, close curly brace. All right, last up today we have Andrew Reed.
What are the odds? Okay. All right, it's a lightning talk, so I will proceed. Oh, there we go. Apparently, I just had to hold my mouth right. Not that I have all that many slides. Anyways, I'm mostly here to plug my poster. Owing to some kind of error somewhere, possibly mine, possibly the organizers, my poster is not in the printed edition of the program. It is in the online version, and you're going to hear about it now. My name is Andrew Reed. I'm a physical scientist at the National Institute of Standards and Technology, and I am one of the principal authors of a project called OOF, which stands for Object-Oriented Finite Elements. And I have here a rather dull bulleted list of some of the things that I think are interesting about it. The things are more interesting than the list. OOF is a material science-focused finite element tool. The purpose of it is to bring push-button access to sophisticated mathematics and computational algorithms, such as GMRes solvers and various other kinds of things, to a material science audience. So nobody in this room probably is our target audience. We are targeting material science domain experts who want to do computation but are intimidated by the existing available tools. Our scope is essentially all of material science. It's essentially a finite element PDE solver that is as general as we can make it. We are a relatively small team, but we have big ideas. The program is written in a mix of Python and C++. It's glued together by Swig, which kind of dates it a little bit, and that's kind of what I put in my abstract that I submitted here and what I think is an interesting aspect of our experience. It is, as I say on the bullet point there, SciPy in spirit, if not in tools. The parts of the program are as much as 15 years old. When we made a number of the calls that we made on how we were going to architect this system, a number of the tools that the SciPy community has developed didn't exist. And so we have, in some cases, proceeded without them and had to kind of make our own call on when to preserve legacy tools and when not to. It's been a pretty interesting experience in code management and doing science. I'm doing these in the wrong order, aren't I? So the new thing about it is a fully 3D code version of OOF was released at the end of the last, anybody who works for the federal government will recognize that date. That is the closing date of the previous federal fiscal year. So we made our target. And as I think I already said in part, the long-term development of this system has had a number of interesting challenges, and I invite you all to come talk to me and see our poster. The poster is actually fairly generic about OOF because trying to capture this kind of information in poster form proved to be more of a challenge than I was able to meet. Speaking of the team, there they are. That's it. Thank you.
Thank you, Andrew. Like I've always said, you can't do material science without making a few eggs. So. French pun. All right. Just a couple announcements before I let you all go. So there are poster presentations in this room from 6 to 7, as Andrew just mentioned. And then there is the annual reception and job fair from 7 to 9. That should be a lot of fun, even if you're not looking for a job, if you just want to be received, I guess. And then registration for tomorrow's Riverboat cruise is now sold out. So sorry if you wanted to go on the river. You'll have to do that some other way. All right. And anything else?
I did have one more thing. So the videos from today's talk are going up on a SciPy 2015 playlist right now. We've already got up most of the ones from this morning. Thank you to the video team in the back here. So I've tweeted out the playlist on Twitter, and I will get it up on the homepage of the website as well. So you can go there and get that. Also, all the GitHub repos and materials for the tutorials are also up on the website. There's a tutorials resources page. The tutorials, it may be tomorrow before we get some of those up because they're much larger files, but those will be up tomorrow as well. So enjoy.
Thanks a lot, everybody. See you tomorrow.